So I'm doing now part 3.1 of lab 21, and so this is building an NMOS inverter. So it uses a single N-channel MOSFET with a pull-up resistor. And the way this circuit works, it's a logical inverter. So when the input is low, the MOSFET is off, so it behaves like an open circuit. And then the output is high because it's pulled up to 5 volts through this 10 kilo ohm resistor. When the input is high, like say it's 5 volts, in other words it's well above the 2.5 volt threshold, then the MOSFET is on, so it behaves like a small resistance between the drain and source. So now the output is pulled down to ground, very close to ground, because this is like tens of ohms compared to 10 kilo ohms. So the output is always opposite the input. So remember the package pins from left to right for the 50N06 MOSFET are gate, drain, source. So I wired up first I wired the source on the right hand side directly to ground, and then I wired the drain through a 10 kilo ohm resistor up to plus 5 volts. I put plus 5 volts here, here's the resistor, and then I did nothing with the gate. So the gate is driven by this yellow wire from the Analog Discovery 2 board, which is waveform generator channel 1. And then it's monitored by this orange wire, which is scope probe channel 1. And then I'm also monitoring the drain, which is the output of this circuit, with the blue wire, which is oscilloscope channel 2. And then so over on the left side, I just have what's left over from building part 2 of lab 21. And then the black wires here are ground, and the red wire is the positive power supply from the Analog Discovery 2 board. And then over here I have the waveform generator, and it is set up just to do a 1 kilohertz square wave, 2.5 volt amplitude, 2.5 volt offset, so that it's just going back and forth between 0 and 5 volts. And it's worth checking before you enable it that the low level is 0 and the high level is 5 volts. Then I go over to scope. Well, also for power supply, I have 5 volts, and master is enabled, and the positive supply is enabled. Then go over to scope, and I'm looking with 500 microseconds per division, and you can see the input, which is at the gate, is my nice square wave. Here, if I turn off channel 2, you can see the nice square wave, 1 kilohertz square wave going between 0 volts and 5 volts. And then channel 2 in blue is the output, and you can see it's a pretty decent square wave. It's opposite, so when the input is high, the output is low. When the input is low, the output is high. It's behaving as a logical inverter. But you can see a little bit of an RC turn on here because the MOSFET channel has some capacitance, and there is finite resistance through which that capacitance charges up when the channel turns on. So then we want to see what happens as we try to operate the circuit at higher frequency. So if I go back to waveform generator, and I go up to 10 kilohertz, and then I go back to scope, and I'll zoom in a factor of 10. So instead of 500 microseconds per division, I'll do 50 microseconds per division. Now you can see it does eventually turn all the way on, but it takes it a while to do so. So this circuit is starting to become not very useful because it really never quite reaches 5 volts, but it gets almost all the way there. We could even zoom in a little more, like here's 20 microseconds per division. And then see if I turn up the wave gen frequency even a little more, like say 20 kilohertz, then I think this is already going to become pretty useless. Well, it does eventually get a little above threshold, but it's already pretty useless because, down for a good fraction of the time when the input is off, the output hasn't yet reached on. So it seems to take this circuit with that 10K resistor. It seems as if it takes it, I don't know, a few tens of microseconds to reach 5 volts. I guess we could make this look even worse if we went to higher frequency. I'm not really sure what the point would be of doing that, but we could go to even higher frequency and it'll look even worse. Yeah, it never gets anywhere near 5 volts now. And I guess one thing that's kind of interesting to try, I actually didn't try this ahead of time. So here we go. Let's go back to 20 kilohertz. Okay, so you can see it has trouble making it. So that's a 10 kilo ohm resistor. And let me just reach over and grab a 1 kilo ohm resistor. And just out of laziness, I'm going to put the 1K resistor in parallel with the 10K resistor. And you know that 1 in parallel with 10 is about the same as 1. I guess 1 in parallel with 10 is like 0.9. So I'll just plug that in here. So now I've basically reduced that resistance by a factor of 10. Or 11, really. And yeah, actually now you see at that same, I think this is a little bit of unstable trigger on my scope, okay. Now you see at that same frequency, which was the 20 kilohertz frequency that was not working too well a moment ago, now this is doing a decent job. So instead of taking tens of microseconds to reach 5 volts, it takes only a few microseconds. Here, let's zoom in a little more and see. Seems like it takes, maybe 4 or 5 microseconds to go from 0 up to 5 volts. Another thing to notice, actually, which is pretty interesting to observe, notice that it's slow to go up, but it's very quick to go back down, and that's because when this NMOS logic gate goes from high to low, you have sort of the capacitance of the MOSFET being very quickly discharged down to 0 through a very low impedance path to ground, because the MOSFET itself, when it's turned on, makes a very low resistance path between the drain and the source. It's like just a few ohms or a few tens of ohms. Whereas if it's already low and then the MOSFET turns off, now you are charging up kind of the electrodes here, their capacitance, through a pretty high impedance path, like a 10 kilo ohm path, or in this case now a 1 kilo ohm path, or 0.9 kilo ohm path, up to +5. So it's that essentially the same capacitance, except for the presence or absence of the conducting channel. It's essentially the same capacitance, but in one case it's being discharged very quickly through a very low resistance path to ground. In the other case, it's being charged up pretty slowly through a high resistance path to +5 volts. So that's why you get the very different time constants for going down from 5 volts to 0 versus going up from 0 to 5 volts. So NMOS logic using just a single kind of MOSFET is it's known to be pretty slow, because you have this effect that things going from 0 up to 1 have to charge through a resistor. So we'll see that CMOS logic is quite a bit faster than NMOS logic. And actually my first microcomputer, a Commodore 64, was based on the MOS 6502 or the MOS 6510 microprocessor, actually manufactured in Norristown, Pennsylvania, not too far from here, by MOS Semiconductor. So it was not CMOS, it was an NMOS device. So that was a pretty slow chip, but that slow chip actually was good enough to power not only the Commodore 64 and the Commodore VIC-20, but also the Atari 2600 game console and all of those old video games from the 1980s. All right, I think I'm already over my 10-minute limit.